Uh, thanks very much, Trideep, for that very, very kind introduction. Thanks, all of you, Jyotishman and others, for inviting me to give the NSF colloquium. It's a real honor. What Trideep didn't mention is 1977, when I graduated from the undergraduate degree, is also my first visit to TIFR. I actually came here for the entrance interviews, and it was every bit as cold then as it is now. Midsummer, and I almost froze to death. And wait, I'm not doing this right. Oh, pick up the wrong one. No. Oh, it's off. Very simple. It was off, that's all. Yeah. So yeah, and thanks a lot. Thanks a lot for coming to the talk. And I hope it doesn't overlap with much with earlier talks I've given on this subject in various rooms in this building. So I've been sort of working on this class of problems for many years, and I'll try to give you some idea actually of early results also, but then mostly new stuff. By the way, I'm also officially affiliated with TIFR in addition to IS. Okay. Things, yeah. So, go. No? Now it'll work. Okay. All right. This is the group currently, and I'll be talking a bit about Roshan's work and a bit about Pankaj's work only, I think, but these are the various other students and the problems they work on. And, sorry, and some of what I talk about was done by earlier students, all of whom are listed here in some form, too many to list. So I'll tell you the systems I've been working on, and I'll try to, I mean, it's a very sort of fuzzy field, but from time to time, we do try to ask ourselves, what are the core questions? What are we really worried about? Because it's also a field in which you can invent fun new problems to work on and maybe give the impression that it's just about finding one more amusing, toy to play with. I'll start by, after my introduction, I'll actually tell you some very early results that have somewhat defined the direction of the field before going into our current research. And then I'll try to suggest what are future directions to worry about. I don't know if I should, maybe this is better. Yeah. Yeah. No, won't work. I have to be there. So. Yeah. So we are all accustomed to studying statistical mechanics, which is the behavior that you get when you have a large number of particles interacting with each other, and the outcomes that you get on large scales in those systems are different from what you might guess at if you just looked at the behavior of the individual particles. The difference between that kind of statistical mechanics and the statistical mechanics of active particles is that each active particle takes up and dissipates energy. And so now you're asking, so each particle is taking up free energy and turning it into work. And imagine you have a situation in which that supply of free energy to each particle is assured, okay? Such as a collection of us each getting our food every day. And then the question is, what is the collective behavior of systems of that sort? In what essential ways does it differ from merely thermally energized matter? And do some behaviors somehow spontaneously come out, which could be thought of as some kind of function, as purposive behavior, as directed motion, and so forth. And, much has been made of this field, partly because the phenomena themselves are very engaging to look at, and partly, I have to admit, partly also because in some ways, it's relatively straightforward to take a problem you have been working on, introduce the active component into it and then asks what happens. That's both a charm and a weakness of the field. There are lots of reviews in the field. I mentioned two over here. You can take a look at them. Excuse me. And obviously, the motivation is that you want to take sort of living, breathing stuff and treat it to the extent possible using the kinds of techniques you learned for the collective behavior of dead stuff. That's the hope. Why is it? Yeah. Now, as physicists, we're interested in ordered states, and those ordered states are characterized by certain kinds of reduced symmetries, certain kinds of preferred directions or preferred structures emerging. So you can classify both the macroscopic states and the individual particles according to the residual symmetry of those particles. You can imagine a system made of particles which themselves have no particular sense of direction in a permanent way, organizing into a state which also is isotropic and characterized, let's say, only by a density change. That would be scalar active matter. You can imagine a more classic active matter system, a collection of creatures that have somehow by interaction spontaneously decided to all start moving in the same direction. That would be characterized by a vector. The descriptor of that state of order, the order parameter, would be a vector. The local dynamics of that system would be described by a vector field. And you can imagine other kinds of systems in which, let's say, the objects that are aligning are elongated. They have an axis, but they don't have any difference between forward and back. So when a collection of particles of that sort condenses into an aligned state, that state is a state of lines. It's not a state of arrows. There's no head and tail. And so the order parameter for that is a traceless symmetric tensor. The vector order parameter goes to itself if you rotate through 2 pi in 2 dimensions. This order parameter would go to itself if you rotate by pi. Correspondingly, the characteristic topological defects of that state and of this state would be different. There was some mathematician in the audience who was worrying me at lunch about the use of the term topological, but maybe he's not here now. Okay, anyway. The other point to keep in mind is, apart from the state of order and the asymmetry of the particles, there's also the dynamic domain in which you operate. You could imagine collections of particles organizing themselves, but their ambient medium just being like a dead solid surface. So that provides an absolute frame of reference. It provides a sink for momentum. Therefore, when they move around, you don't have to worry about balancing the momentum budget. You have a substrate that takes care of it. Or you could imagine the whole dynamics is taking place in a very dynamic medium. If you have fish organizing themselves into a flock in a fluid, then if a given fish decides to change, so even though the fish can autonomously decide to change its direction of motion or its speed of motion or both, it can't do so without obeying momentum conservation. So when you have an ambient medium, the interaction of these guys, purely because of the need to conserve momentum, is very different from if you have a kind of a momentum sink. So we talk about wet and dry active matter in that. You can also imagine that there is a fluid medium and yet the system, but the system is confined between 2 walls. In that case, the fluid still plays a role effectively because the fluid flow is constrained to close on itself. And that defines dynamically a qualitatively different domain. Just to show you some examples of these. This is a state which, at least locally, is described by a vector order parameter. This is an artificial realization of active matter in Nitin's PhD work. Why is it stopped going around? It's not transmitting. It's a fish called Karimeen. It's a fish tank in CES at IISc. Why is it doing this? I think it's not connecting well. Yeah. I certainly don't understand the collective dynamics of this collection of objects. And what's interesting there actually is not so much the orientation as the boundary shape and its dynamics. Something's worth discussing. This, as I said, is a much simpler flocking system. Hey, why is it doing this? Come on. Nah, Sorry, it's a nice movie here. It's just not. No. You think so? Yeah, it's well, I mean, it shouldn't be jerky like this. What I'm just trying, this is a real experimental system, which I will talk about more during the talk. Each of these particles has a vector orientation. As you can see, they're coherently organizing themselves into a globally moving state. But you can have orientational order in a system in which, even though the axes of the particles are aligned, they aren't going anywhere on average. So here what's happening is you've got particles which are moving more back and forth along their length than transverse to their length. So that means if you ask about their kinetic energy, it's unequally distributed between this way and that way. A more delicate way of being out of thermal equilibrium than actually locomoting in some direction. And these systems, which I will not say much about during the talk, are awfully interesting, actually. Anyway. I also want to emphasize that active matter isn't just a sort of weird corner of non-equilibrium physics. Essentially, any system that you take, if you can homogeneously suffuse it with energy, then if there are degrees of freedom that can pick up on that energy, their way of organizing themselves on long length scales is effectively described by the kinds of equations we write down and call active matter. So the zero resistance state of two-dimensional electron gases energized by microwaves has been described by using equations that are essentially the equations of flocking. And many of these exciton-polariton systems have an effective active matter description on long length scales. Or more generally, if let's say you have a 2D quantum system at the interface between two baths with different chemical potential, you just imagine you have a square system like this and you pump energy through it in the third direction. The effective 2D dynamics of those systems is a kind of active matter dynamics. So these connections are worth exploring and people are starting to explore them currently. I won't talk about them during the talk. Now, actually yes? Feel free to ask questions during the talk. After working on this for a few years, in one of the review articles that I wrote, I sort of made the point that, look, all of us should be working on this class of systems. It's kind of an imperative to work on this class of systems, kind of a manifesto. So the idea there was, look, you've got this class of systems. What are the laws governing their steady state distribution? What kinds of phases can they have or can they not have? If you have coexistence of two macroscopic states, what is equalized between them? If you disturb them away from a stationary state, what are the laws governing their relaxation? Is there a relation between fluctuation and response? What are the scaling properties at critical points in these systems? What about the scaling properties in an entire phase in these systems? So all these questions, if you like, this, rather than one central question, the mission of active matter as a branch of statistical mechanics is to see how generally you can answer these questions. And one of the approaches to this is to start with a particulate description and do a microscopic theory. The other is to say, if I have a system in a given state of order, I know what variables to use to describe it directly in a coarse-grained theory. So I close my eyes, I write down a coarse-grained, quote-unquote, hydrodynamic theory, and use the general principle that anything that's not explicitly forbidden by some symmetry rule is allowed, and then write down a coarse-grained description, and then see what comes out. So this is the approach that we have taken. The funny thing is, decades before we started working on this stuff, it turned out that serious, grown-up fluid dynamicists in chemical engineering had already started worrying about this. And there's this really amazing paper where they even use a term that we thought we had invented. So they stole it from us retrospectively 30 plus years before we did. Yes. So the point is, there will be, that is, if you have a system that, let us say, has scaling properties and it's described by a few coarse-grained fields, you will find that they fall into universality classes. Indeed. Yeah. And for reasons, meaning that for specific models of active matter or non-equilibrium systems, you can write down stochastic PDEs or microscopic models and analyze their scaling properties using the machinery that we know from critical phenomena and so forth. And you will find it falls into universality classes. Yeah. Yeah. So I'll say a little bit about that, but that's actually okay. I don't want to trivialize that question. What we have done so far is to say that we can't see any reason why there will be different rules for selecting the slow variables. You know that if you have a system governed by conservation laws, then the local densities of those conserved quantities are slow because at zero wave number, they don't relax. Therefore, at long wavelengths, they relax slowly. So that's one set. The other is if you've spontaneously broken a continuous invariance, then the Nambu-Goldstone modes, the long wavelength variations, which in the limit of infinite wavelength become a symmetry of the system, is another set of slow fields. Then perhaps you're actually at the threshold of a phase transition, of a continuous phase transition, a supercritical bifurcation. Then the order parameter itself becomes a slow variable at that point. So we have proceeded on the assumption that there are no other reasons to have slow variables. We don't know that for sure, and I'll comment on that at the end. So what we say is the rules for selecting variables are the same ones, but the kinds of terms that enter the equations of motion, now that you're liberated from time reversal invariance, are new. And that's the thing. That's where it comes from. So these guys said that, look, if you've got matter inside which energy conversion from chemical to mechanical is taking place, you should be able to see spontaneous movement in these materials. This kind of thing should be happening in living matter. Folks, you should work on this. This is a new kind of complex fluid physics. This is new kind of statistical mechanics. And so these guys wrote a magnificent paper which everybody ignored. Possibly because some crucial mathematical and physical machinery had not yet been defined. The idea of how to write down hydrodynamic theories of broken symmetry systems. Basically, it is a few years before Martin, Parodi, Pashan, Halpern, Hohenberg did their work. And somehow this work sank without a trace. It's very strange. So in fact, the specific model that they proposed in their paper, in modern terms would be called, but there was a classification of dynamical critical phenomena problems by Halpern and Hohenberg in the 70s. And model H was, you've got a scalar order parameter like a composition or a concentration field, and you've got a hydrodynamic velocity field. This order parameter produces stresses that make flow. That flow advex this order parameter. They called it model H for hydrodynamic. Introducing active forcing into that system would turn it into something which now we call active model H. In effect, these people anticipated exactly that model. They didn't talk about fluctuations, stochastic dynamics, but in average sense, they had those equations. Okay, but somehow nothing happened. All right, excuse me. Let me tell you a few sort of landmark results in the field. One is, as you know, if you write down either a computer model of agents that try to align with each other and don't get too close and don't get too far or something, then if you increase the concentration and or you reduce the error they make in aligning, you go from a disordered state to an ordered state. And this is actually experiments on keratocytes. And this was defined as an agent-based model by Reynolds and therefore was named after Vicek. It was then turned into a field theory by John Toner and Yuhai Tu. The point I want to make about this work is many of the claims and beliefs about this work have proved not quite true. There is a phase transition, there is an ordered state. People thought they knew the scaling properties of the ordered state exactly in 2 dimensions when at the time the model was formulated, and then they corrected it 10 years down the line, 15 years down the line, and even that is wrong. So we and a few others have contributed to setting this field back by 20 years by showing that various things we thought we knew are in fact not true. So we've tried to make the case to the journal. Normally you tell a journal that you've significantly advanced the field. So we've explained to the journal that we've retarded the field, and we're hoping that this will somehow get them to agree to publish it. Anyway, well, these are flocking models, and leaving aside that issue, which you can read about in this impossibly difficult paper of ours, what we asked, and sort of really our first entry into this field, was to say, okay, you have flocks, but you've just made up rules for flocking. You haven't respected the laws of mechanics in saying how something aligns with something else. Typically, this whole process takes place in a fluid medium. So if you want to write down a theory of that system, the slow variables include not only the concentration of the particles, but the velocity field of the whole system, because it's a momentum conserving system. What happens when you do that? And what we showed was that at least in the strictly viscous limit, aligned states are completely impossible. Any aligned state you produce, if you disturb it slightly, will undergoes a hydrodynamic instability, which results in this state that people discovered in these beautiful experiments on that Zvonimir Dogic discovered, a kind of weird turbulent-like state. You can also see what happens to this phenomenon inside a cell, and this same instability inside a living cell causes flows that turn the nucleus round and round, as showed many years ago. The equations that we built, which showed this instability, can be called the equations of active liquid crystals, or the equations of an active gel, and those equations were later shown also to describe the cytoskeleton, which is the filaments and motors inside a single cell. Somewhat more recently, this was a couple of decades ago, we showed that this magical instability is actually just one end of a much richer behavior. So if you include the inertia of the fluid in your theory, then what happens is this instability, rather than being instantaneous, remember, Stokes hydrodynamics is like Newtonian gravity. You specify the forces everywhere, you know the velocity everywhere right then. If instead you at least allow the fluid to communicate its velocity field via the diffusion of vorticity, if you do unsteady Stokes hydrodynamics, then the inertia of the fluid matters. And then what you find is that there are two speeds. One is the speed at which the flock is moving. The other is the speed at which the instability invades. And that speed is proportional to 1 upon the square root of this density. And the competition between these two speeds says that you can move fast enough to escape this instability. So the flocks in fluid with inertia can exist, are not necessarily unstable if you're swimming fast enough. You've got an invasion speed, you've got a swimming speed. If you swim fast enough, you can escape the instability. And there's a nice phase diagram, which I won't say anything more about. This is still my opening summary, unfortunately. Another sort of key result was that if you now forget about the fluid and now forget about a vector flock. Imagine your flock, your aligned state is a nematic. That is to say, it's got an axis, but neither head nor tail. I mean, no distinction between head and tail. The characteristic topological defects there are of this sort, where you either go around by minus pi as you circle a point, or by plus pi. And we predicted that these defects, the plus half defects, are motile. We predicted it and we confirmed it in experiments. And this has been what. See it. Excuse me. Weird, huh? No. I'm just trying to move the little arrow to make contact with the little movie here. Don't know what's going on. Now I found it. I don't know what happened. Now does it work? Will there be a movie? Okay. Movies are not going to work today. It's all right. It's not. It doesn't matter. Don't worry about it. We'll move on. Otherwise, I won't get to any of the new stuff. You can. Yes. So this experimental system I'll say more about, but imagine you've got those funny particles I showed you that go back and forth more than they go sideways. If you pack them at high enough concentration, they form a very dynamic aligned state whose topological defects are of this type or of that type. This is all really old work, but I'm just trying to tell you some of the important things in the field. And these guys have a vectorial asymmetry. These guys don't. Therefore, we predicted these guys should be autonomously motile. And this series of stills shows you this guy moving in a given direction. And that means that topological defects become an effective self-propelled particle on its own. So even though the phase has no vectorial asymmetry, objects with a vectorial asymmetry propel themselves and run around. And there's a nice statistical mechanics of those, which leads you to a modification of the classic vortex unbinding theory of Kosterlitz and Thouless as applied to these systems. They still know. The point is that on the one hand, they have an interaction, which when they're close is like this, like the Coulomb gas thing. On the other hand, the plus guys are autonomously motile. So you might think they should always be pulled apart. That's a whole seminar. Let me not start. Okay. Another phenomenon, another sort of really important phenomenon, which was not something we contributed to, is that now supposing you consider particles, each of which moves persistently in a given direction for some time, but changes direction quickly. And imagine there's no aligning interaction. And imagine there's nothing else. Imagine you just got a bunch of disks, each of which has a little arrow on it, and that each of those arrows moves in some direction, but slowly loses its way. They have excluded volume, they can't occupy the same space, but they have no attraction, they don't know each other's presence until they make contact. This system, as a function of, let us say at fixed self-propulsion as a function of density, or at fixed density as a function of self-propulsion, undergoes a condensation, undergoes a transition with all the properties of a vapor to liquid phase transition. Not because they attract each other, but for the same reason as when you have a large crowd, people take time to turn around and get out of each other's way. If before they turn around and get out of each other's way, there's more incoming guys, you get condensation. And it's a bona fide phase transition. It really has all the properties of vapor to liquid phase transition. It has other properties that are subtly different. But so I think I mentioned these three effects as these three classes of phenomena as some of the important results from the early to middle years of active matter. Let me tell you the kinds of things we're worrying about now. Remember, I told you about flocking models, things that line up with each other. You can turn those agent-based models, as Toner and Tu did, into a continuum field theory. It's a theory of a vector field V, which you can think of as the orientation or the velocity field of these particles. Okay. Supposing I take a super simple description where I forget about their density. I don't make it incompressible. I throw away their density. I introduce birth and death or something and throw away their density. I have just a vector field like this. If it was just a bunch of vectors trying to align with each other and locally having a tendency to form a non-zero movement, then you would have this term which favors a non-zero modulus for V, right? Remember, this is dV over dt equals various things. This term says I want V magnitude to be non-zero. This term says I want neighboring V's to point the same way, right? This term says random disturbances agitating the V's, okay? Now, but these guys are velocities. So because they're velocities, if locally there's an inhomogeneity, they will carry that inhomogeneity, right? So this term. Without this term, without this lambda term, this equation is essentially the equation, the dynamical equation for planar spins. That model is known to have a very delicate kind of phase transition, which I'll talk about in a minute. If you take this equation, so let me actually go to that. Where's it gone? All right, it comes later. Doesn't matter. Supposing you just take this equation and look at, supposing you assume that you're at low enough noise that these guys are all lined up. Then in the absence of this term, it turns out the angle fluctuations are so big that the ordered phase isn't truly ordered. The probability that one guy is pointing a distance r away is pointing the same way as another goes to zero very, very slowly with distance, algebraically, but goes to zero nonetheless. The stiffness is non-zero. Toner and Tu showed that the presence of this term makes the system actually have true order. That is, say, the probability that two guys infinitely far apart are pointing the same way is non-zero. Okay, that's the ordered phase. Now, the question is, okay, you have the order phase. Can you calculate the scaling properties of this ordered phase? So you take this equation and you look and write down an equation for small fluctuations about the aligned state. Write the velocity as this guy, ignore fluctuations in v, worry about fluctuations in the angle. And you get this equation plus higher order terms, which turn out to be unimportant. The kinds of things that you're interested in, when I say scaling properties, what do I mean? What I mean is if I calculate statistical properties like correlations in the velocity at different places and different times, you can show that they obey a homogeneity relation in the sense that if you scale the transverse coordinate by some factor b, the coordinate along the ordering direction by a factor b to the zeta, and time by a factor b to the z, then those correlation functions transform to themselves. But then you would like to know what are the values of z and zeta and chi. You have to scale the field as well. It was thought that you could do this exactly in 2 dimensions. So the negative result I mentioned that has set the field back about 20 years is that we've shown, I think, really convincingly that you can't do this exactly in 2 dimensions. So I won't describe the algebra that shows that you can't, but in a sense, it's a major result in the field because something we thought we'd sorted is no longer sorted. So we don't know the scaling properties of the simplest flock in 2 dimensions exactly. You can do a calculation near 4 dimensions in 4 minus epsilon and get results, but you cannot transport those to 2 dimensions. And essentially, it's because people had failed to notice a second relevant nonlinearity. So that's, you can read about, those of you who are nerdy enough to care about this can read about it here. Okay, so that's one important new result. Sorry? Yeah, so you can look at it the following way. If you take this equation, you can view it as non-equilibrium in 2 different ways. One is if you think of it as a fluid, but a weird fluid, then this part is just an ordinary property of a fluid. It advects itself. But this part, creating a local velocity out of a zero velocity state, means it's self-pumping in some way, if you think of V as a velocity. If you think of V as an orientation, then this part is just standard planar magnet physics. But orientation that advects itself, what the hell is that? That's weird. I will come back to one way of getting such an effect. So depending on your point of departure, it's a weird marriage of a fluid and a magnet. And if you make it just a magnet or make it just a fluid, it's equilibrium-like. Yeah. Yeah. You can think of it, no, but remember, it's not a sink, right? Because the way it's written, if A is positive, it means the V equals 0 state is unstable to a spontaneous production of V. So if you think of it as a reaction, advection, diffusion problem, where V is the quantity that is being produced by the reaction, this is the reaction term, and this is the saturation term. This says I'd like to have V, and this says how much V I'd like to have. That's one way of looking at it. And then the fact that this thing is a V, is a velocity, means it carries itself. And the fact that it has interactions with neighbors makes it spread. Okay, so that's one way of viewing it. But if you think of it as just a bunch of rotors that are pointing randomly, then this is just the term that makes this physics is what you would get if you started with a microscopic statistical mechanics model of a bunch of rotors that like to point parallel to each other but are subject to noise. Then you would never get this. So it depends on how you view it. Sorry, this is becoming a primer on the subject. Maybe that's more useful than the hot latest results on it, for those of you who haven't listened to my talks before. Anyway, so this is one fun thing that happened relatively recently. So now, let me sort of move to a topic that will prove to be related, which is non-reciprocal interactions. Supposing you've got two objects and there's some distinction between them, you can easily imagine in social situations or in other kinds of settings that one of them is attracted to the other and the other is repelled by this one. Nothing wrong with it. But clearly, if you had interactions that were governed by a potential, that is, say that if the force A and B exert on each other is because of a potential energy of interaction of A and B, you'll never get that. If you take a collection of particles in a driven state, there's no grounds to expect that the effective interactions in these degrees of freedom is governed by a potential. So in general, for out of equilibrium systems, you expect non-potential interactions, and you expect that non-reciprocal behavior would be generic. More specifically, in the living world, it's natural to think about them. You can also think about it in biological systems like neural nets, in essentially any kind of signaling based interaction. If you've got a ligand and a receptor, then it may be true that binding is governed by a pair potential, but the signaling that results thereafter means that the effective outcomes are far from those that come from anything governed by a potential. Now, in general, people, when describing the subject of non-reciprocal interactions, are fond of saying that any mediated interaction is non-reciprocal. And this is actually deeply misleading, because even the fundamental interactions in nature are mediated by gauge fields. That's not the point. The point is the following. If you've got objects, so let's take a specific example. Suppose you've got two objects which each of which moves in a direction that is set by its shape and its orientation. But imagine that which way it points is influenced by its neighbor. So then you can imagine this guy likes to point to that guy. It can move in a certain direction. So if you separate the force, the motive force which actually propels something from which way it aligns, then you can get these kinds of behaviors. So this is just a caution if you look at the literature in not taking this notion that mediated interactions are the reason for non-reciprocity. In that case, everything would be non-reciprocal. So suppose you consider a bunch of particles in a fluid. Brownian particles, thermal equilibrium, interacting by some pair potential. And there's a fluid medium. So the actual way they interact is that something moves, it moves the fluid, it moves something else. Regardless of the dynamics of the fluid, if the system as a whole is at thermal equilibrium, then if you monitor only the particle position degrees of freedom, their dynamics will obey detail balance. And regardless of the fact that each particle's momentum is transmitted through a fluid medium, the dynamics of the particle configurations will be reciprocal. Then that's different, because then you're out of equilibrium. So the point is, what's crucially important is a sustained dissipation of energy. That's not. Yeah. Let me skip this. Yeah. So let me talk about interesting realizations of, I have to stand here. Interesting realizations of non-reciprocal interactions. So this has been our favorite experimental system for many years. Currently in a lab, which, this is in collaboration with Ajay Sood, but it started earlier with friends in chemical engineering, collaborations with Narayan and Menon, and so forth. So this is a very macroscopic system. Each particle is like half a centimeter long or something, okay? And about a millimeter in diameter. And you can create fake, but actually authentic recreations of self-propulsion by this system. So you have this whole thing, you shake it up and down. Each particle has a shape, and there's a little bit of room to move around. So you do this, and the particle will end up walking. I'll just show you what, hopefully. Oh, I think the movies are not going to work, right? Let's see. Let's see if it works this time. Okay, it's slightly calamitous. Let's see. How about here? Maybe this will work. No. Does this work? It's kind of weird that it's very weird. I tried. Control click to open hyperlink. Okay. Okay, it's kind of a very jugadu way of doing it, but it's okay. So what you have here is, you're looking at it from the top, you're shaking up and down like this. This particle has a little room above to wiggle, and it walks. Okay, so my claim is that this is not just a silly toy, it's a valid recreation of self-propulsion. Because you're homogeneously energizing the system, that's like a nutrient or something bath, and each particle is picking up that energy because of its shape and because of its coupling to the base, and it's walking. So I should be able to test theories of the kind that I've been talking about. Gravity and density gravity is, this experimental system is confined like this. There's just a little room to move up and down. Motion is in the horizontal. Yeah, moves in the horizontal plane. So it's a classic, I am pumping energy in a third direction, and I'm monitoring the dynamics in the two perpendicular directions. So as far as the physics in that plane goes, it's a system with a sustained energy throughput in a third direction. And so you can use this, you can sort of use this as a nice way of, how do I get rid of this? There's some way of getting more. Hide floating meeting controls. Yeah, okay. Now I go to slideshow. That's somewhere, is it? There. Yeah, okay. So I showed you that. And in this system, yeah, so the mechanics is really this. You shake up and down, and because of any kind of mechanical asymmetry between the two ends, different static friction or something, they'll start walking. Okay. And you can, if the two ends are the same, then you will get the behavior I showed you in those headless particles. If they're spheres, then they'll go nowhere because the dynamical mechanism has to do with tilting, and you tilt a sphere and it doesn't know it's been tilted. So it won't go anywhere. There are spherical systems that propel themselves, but that's another story. I'll talk about it later. Skip this also. So I'll just tell you a story. I really hope I can show you this. This is, come on, go back. This is Roshan's PhD work, Harsh, Rahul, and Ajay Sood and all. And now, again, it looks like I'm going to have to do this. Now it's good. So what you can see is that as a function of, I'm keeping the concentration of these long, pointy, motile particles constant and changing the bead concentration. And I'm going from things moving around. So isotropic to time lag is also killing me. Okay, so the lesson, I guess, is that this Zoom way of presenting the talk has real problems for movies. What to do? Sorry? No, but if nobody is watching on Zoom, it's fine. But if you disconnect the Zoom, you have to connect the computer. So right now, the only connection is this. Yeah, it's a pity. I see. How do I? Okay. Stop share. And custom live. Let's see.
Yeah. So yeah, on the right there, you see optimize.
Thank you.
Yeah.
Let's see
Now
if this
you
works.
click off the sound in case there's sound.
Yeah, who knows? Yeah. Share. So let's see if this works any better. Thank you. So now you see that you go from sort of random motion to show the movie, and I'm not going to get to the end of my talk. Yeah. What I want you to watch is not, the image is not very good, but you will see in a few seconds that these guys, these pointy guys start pointing that way here. Yeah, and the end state anyway is that these guys and those guys condense a bulk quantity of these into a single region. So enough of these particles just to fill an interface, seemingly a sub-extensive number of self-propelled particles are able to condense an extensive number of non-self-propelled particles. So some funny kind of phase transition taking place here. Yeah, you can see something similar here. So you can get either one row of these guys pushing a bulk quantity of self-propelled particles, of non-motile particles. Where is it? Yeah. So you can see this tiny few guys just assemble into a row and they push all of these coherently, or two such sets assemble into two rows and condense a bulk. So you're getting a sort of condensation of non-motile particles due to a tiny concentration of motile particles. Now, it's not absolutely clear that this can take place to an unbounded quantity of non-motile particles, but there is a very interesting instability of a mixture of motile and non-motile guys into a state, into a kind of condensation. So I have now used some judgment. I can tell you very quickly a simple theory. Basically, there's two parts to the story. These guys push the beads and they create a density gradient. These guys then, because of their slightly asymmetric shape, are more easily accommodated with the fat end in a low density region and a skinny end in a high density region. So this two-part story, one, that the motile guys push the non-motile guys and create a density gradient, and two, that the way they are oriented with respect to that density gradient happens to be the way they are actually very happy. In other words, the steric interaction of the shape with the density gradient is precisely the one which is favored. Okay, movement creates a density gradient, and their shape is such that their steric interaction with the density gradient favors sitting in that manner. So, and it's naturally non-reciprocal. So this is a realization of a non-reciprocal interaction, because on the one hand, the rods point and move towards the beads. That means the rods are in effect attracted to the beads. On the other hand, the beads are being pushed by the rods, the beads run away from the rods. So non-reciprocity, rather than being some deep and mysterious thing, is a trivial consequence of motility and excluded volume. So you can do a more serious theory of that. You can write down continuity equations for the densities of rods and beads, and you can. Yes.
The direction is set by the orientation of the particle.
Yeah, right.
You have two sets of particles, one moving in this direction, another moving in direction. You're going to get a high density phase here.
Yes.
Once you get a high density phase, then we can't move. So what was the surprise in this?
The surprise is that this thing doesn't dissolve. Why don't these guys turn around? No, they're at the periphery. Why would they not turn around? So the robustness of the phase separated state in a one-dimensional system. So you've got a high density and a low density region. You've got a little kink, but you've got a little density sharp gradient between them. That sharp gradient can be dissolved by just these particles turning around. That's, after all, why you don't get phase separation in one dimension normally. And there isn't an infinite barrier to these guys turning around. There's just yeah. Yeah, but why should that survive? Why should that? No, I mean, that's, you're saying, but it's actually not an absorbing state. So you're trying to, it's actually not it's not an absorbing state. There's actually exchange. So these are details. There's actually exchange of particles even through that. Yeah. So it's not as simple as an absorbing state into which it gets stuck, because were it an absorbing state, you might get a wide variation in how much stuff you capture. You don't. You get a reproducible amount of condensation. So it's something like a phase diagram. Yeah. So I mean, you can write down a PDE in which the orientation of the rods produces a current of the rods and of the beads, and you can discover a density instability coming from the mechanism I just described. But it's a pity I sort of not sure where the time went for talking too much. So what you get is an effective theory of the density of the beads, in which the tendency of the rods to point towards the beads and the tendency of the rods to push the beads go together to effectively reduce the diffusivity of the beads and potentially drive it past a threshold where it gets negative, thereby creating condensation. So that's that part. You can even work out you can ask how big a batch of particles can these motile guys push. And what you find is that the only thing that limits it is how compressible the bunch of particles is. As you pack them, they effectively become like an incompressible mass. And then for all practical purposes, you can push an unbounded stack of particles. So the decay you can work out the density profile of this moving state. Where is it? Next page. Yeah. You'll find the density God, this lag is driving me nuts. Thanks. You'll find the density profile decays with a length that gets bigger and bigger as the compression modulus of the bead pack gets bigger and bigger. So you can, in some sense, it's a little bit like, when you're pushing stuff using, when you're moving stuff on a floor or something, you can push things as long as each thing that you're pushing pushes the next thing in front of it. This mechanism, or something very much like it, seems to be operating in actual biological matter. In these what are called motility assays, you have molecular motors on a surface and microtubules, which are the filaments on which they walk. Actually, I won't discuss any of the other topics. It's okay, right? Strewn on top of them. And if you have two species of motors, one of which likes to walk one way and one of which likes to walk the other way, you end up getting structures in which the microtubules lie like this and segregate macroscopic regions of the blue and the purple motors. Very much, the only difference is here you have two species of motors. In our case, you had the thing that distinguished the two sides was a high density and a low density of one species, which you can think of as particles and holes. And one species likes to walk this way, one species likes to walk this way. You end up getting structures that resemble the structures we had in our study. The difference is, as far as I can tell, in these guys' work, you don't get just one layer of filaments separating two essentially unbounded layers of motors. What you get is striped phases. We do not understand why we don't get finite wavelength modulated phases. Normally, if you have a system that's undergoing what is called a spinodal instability, at least at onset, you get striped patterns. We've tried very hard looking for them. From the theory, I'm unable to tell why you shouldn't get them. That's a mystery. I think I'll just skip ahead to the end because I'm supposed to shut up at 5 o'clock. And so I won't tell you about odd mechanics. What's this? Okay, so I'll summarize. I only told you one out of the 3 topics I was going to talk about. I told you about flocks and how we don't understand their scaling properties. I told you about a new kind of phase transition driven by the non-reciprocal interaction of motile particles and non-motile particles. I did not tell you about these other topics. There's lots of open directions in this field. There's lots of challenges. The fluid dynamics stuff I told you at the beginning, the physics of what happens when you introduce inertia is largely open. The idea of marrying simple self-propelling properties to actually delivering stuff, to transmitting information, control, information processing is another open direction. The possibility of writing down theories of evolvable active matter is still something that people are working on. More general sort of physics theoretical questions. One is a more general predictive hydrodynamics of powered matter beyond the simple systems we've seen. We've made substantial progress in this direction, of which I really only told you the beginning part, instabilities and non-reciprocity. We really haven't started to confront sensing and signaling. We also haven't understood the following very general question. You can have a collection of particles moving around because it's. Let me backtrack a little bit. Let's take a different system. Let's not think of active matter. Suppose you have a layer of fluid heated from below. Okay, if that layer of fluid is thin, you can send a heat current through it, and nothing interesting will happen in that layer of fluid. But the fact that you're sending a heat current through it means that the system is in a state of broken time reversal invariance. Okay? When does small-scale breaking of time reversal invariance result in macroscopic manifestations? This is a question which in the fluid dynamics literature is well understood. It's when does a conducting state give way to a convecting state? More generally, therefore, understanding an active matter when broken time reversal at small scale, which is merely the defining quality of active matter, affects large-scale behavior, I don't think we have a general understanding of it. Another question you asked me about, how do you choose the effective slow variables? I don't think we know beyond the principles I told you, which are the ones that you apply to sort of dead matter, but you can't rule out the possibility that living matter or evolved matter has ended up at a very non-generic point in its parameter space. If it has done so, you can't rule out the possibility that modes of excitation which were normally fast could become slow. It would be nice to have a simple model theoretical system on which to test this idea, where you evolve by selecting for something and see if you end up somewhere in parameter space where maybe new slow modes emerge that you could not have guessed at on general grounds. I think a very fruitful direction for the future is to look at the connection between the kinds of active matter models we write down and driven quantum or optical matter. And there are discussions going on in that class of problems. There's also loads of purely technical challenges. When I say technical challenge, I mean, can we calculate the scaling properties of this or that phase? What is the nature of the phase transition? Problems that are rooted in the kind of physics that we've always done, but now doing it for these active systems. Those are abundant, and we don't know. It's not very clear that new concepts are required. It's more like new, hard field theory challenges. Okay, so I'll stop with that. As I said, for reasons that partly had to do with my struggles with trying to show you movies, but partly my chatting too much in the beginning, I ended up not telling you much of what I was going to tell you. But I hope what I told you was interesting. Thank you.
Any questions? Your comment about fluid dynamic system where it's fast heat, and at some scale you're globally convected.
Right.
Fast heat at the system, then you will get convection at a short time scales. Small length scale. Why should it be that? I mean, I can understand the global irrelevant convection being happening at some critical phenomena, critical temperature gradient. Why should even small cells not happen? Is there a particular?
I mean, the point is, remember that when you write down fluid dynamics, your description is at a scale much bigger than the mean free path for the system, right? So on the scale on which the velocity field is defined, you know how to write down the equations of fluid mechanics, and you know there's an actual threshold. Now, it may be that if you take Rayleigh-Bénard plus noise, you will find that there are small scale fluctuations. It's not very clear what noise to put in there because the noise has to be coarse-grained out to the, sort of a mesoscale that's not a molecular scale. Okay. So, I mean, you can certainly, by all means, you can write down Rayleigh-Bénard plus thermal noise. Okay. And then what you will find is that it's vaguely conceivable that you will get some velocity field fluctuations on minute scale. You can argue that as you approach the threshold, the system will be very sensitive to any kind of noise, and therefore you'll start to get slightly larger fluctuations. There is an interesting story associated with that, which I can tell you later. But it's like any hydrodynamic instability. Basically, you see nothing of it until you reach the instability. If you deliberately put in noise into those equations, so take any equation you like with a continuous onset of some flowing state, moving state. If you put in noise, you will get some fluctuations. Yeah. Yeah.
Here, the presence of no stabilizing factor, which is gravity. For horizontal flow, there is no onset.
No, but that's a different question. I'm talking about a system with a threshold. If you have a system with a threshold, because the variables you're using are actually, these are seriously macroscopic, it's not exactly the same. What is a good way of putting it? Okay, let me tell you the correct statement. I have never tried to write down the equations for Rayleigh-Bénard convection plus thermal noise. It is possible that if you do so, then at onset, you will have appreciable fluctuations. Okay. But in fact, what happens in those systems is if they're susceptible to macroscopic movement, then ambient noise also disturbs them. And there's actually a famous story of, I think, Gunter Ahler's experiments where they were studying the onset of Rayleigh-Bénard by some light scattering, and they started to see enhanced light scattering on a ring in Fourier space. And it turns out the source of that was not thermal noise, but ambient noise. So you could basically take an equation with a continuous onset of something, put in a noise. Then, because you know the response function is getting big at onset, if you put in a noise, the response to that noise will get big at onset. The amplitude of fluctuations will get big, but I think it will do so in a very facility-dependent way. That's what I suspect. There's a history of this also in turbulence, other turbulence problems. Okay, actually the only phase transition I managed to show you was this weird sudden segregation. As far as we can tell, it's not continuous. We haven't been able to explore parameter space enough to find, the spinodal, the coexistence curve, any of those things. But it looks more like ordinary condensation. And ordinary condensation, except at the critical point, isn't continuous. It's abrupt segregation into one density and another density. We never reach a place where nearly equal densities are, I don't know, we don't know what to tune to move along a coexistence curve and reach the critical point in this problem. That we don't know. The equations theoretically will allow it, but it's more. So in this particular case, it's something really stupid. It's literally that you've got this thing lying on the surface. You may remember in high school physics, they tell you if you have a rod like this and it falls and there is no static friction, then the center of mass will not displace, right? So now introduce static friction. you toss it up and it comes down, generically the center of mass will displace. And so if you have an object whose two ends are different, then shaking up and down ends up resulting on average in motion in one direction. And then that direction changes because of noise. So that's actually what it is. Huh. No, but you don't need that. You account for that difference in the two ends by saying that the descriptor of the aligned state is a vector. That is, you say each particle is associated with a little unit vector. You draw a coarse-graining volume, coarse-graining area region around it, and you say the average of all those unit vectors is a vector, which is the polarization. So the fact that the individual particles are vectorial translates into the fact that the aligned state is described by a vector order parameter. That's all that hydrodynamics has to do. It coarse grains, it doesn't worry about the particle beyond knowing that it's got some sense of direction. You put it together, it becomes a polarization. That's actually how it's done.
What is the chiral matter which is said?
Yeah. I can show you one slide or something on it. So let me first tell you the following, that supposing you write down a dynamics in which you ignore inertia just for simplicity, you have a bunch of coordinates, and let's take a very stupid dynamics. There's a damping and there's a purely quadratic, there's a purely linear force. The damping linear in the velocity and the restoring force linear in the force. This problem, if this is a real dissipative coefficient and this is a real elastic constant matrix, can't oscillate, right? Because K will be symmetric because it came from the energy function. Gamma will be symmetric because of Onzaga. Okay. So now, supposing your system has, supposing your system has an odd component to K, then what will happen is X1 and X2 can have a coupled dynamics in which K12 take it to the extreme case in K1, in which K12 is the negative of K21, or at least has the opposite sign. Now, why would that happen? The way to see why that would happen actually requires it'll require a few. I'll have to give the talk. I'll show you. Okay. But the interesting thing is, in these active systems, if you have a system that has a displacement field, maddening, sorry. Yeah. You want to know microscopically what physics gives it that. I mean, it's actually really simple. If you have a system that's chiral and active, then generically the individual components are spinning. Okay, so if you have a bunch of spinning things, then it's easy to see why this will come out. So almost any of this active stuff is actually that microscopically you've got some kinetics going on, which manifests itself macroscopically as forces apparently coming from coordinates. They're all forces coming from hidden kinetic energy. Okay, and if they're spinning, then you get this. And actually, this odd mechanics has long been explored again in fluid mech. When you take a Rayleigh-Bénard problem and let's say you form a cellular hexagonal and you have a magnetic field or you have rotation, you get odd elasticity there. All that mechanics is already worked out like 25 years ago before it became famous. So not all. I mean, I'm saying a lot of it. A lot of this stuff. If you go back to the pattern formation literature, if you go back to hydrodynamic instabilities, many of these ideas are already there. And actually, some people in those fields point out very correctly that some of the more modern practitioners don't remark on this. Hey, yeah, it's I didn't expect it. What to do?